Are you tired of the visible layer lines and stair-stepping ruining the surface quality of your 3D prints? Well, I've got good news. True 3D printing, also known as non-planar printing, is becoming more accessible than ever. Thanks to a new slicing approach developed at ZHAW, you can try it on your existing machine. No fancy hardware upgrades needed. You can even use ironing for super smooth surface finishes. In this video, I'll show you how I got non-planar printing working on my standard setup and how you can do it too. Let's get right into it, here at JanTec Engineering. Thanks to PCBWay for sponsoring part of this video. If you've been into FDM 3D printing for a while, you've probably already heard about non-planar slicing and printing. Traditional slicers do exactly what the name suggests. They slice your 3D model into flat, horizontal layers that are getting stacked on top of each other. That's why this process is sometimes called 2.5D printing. While this method is simple, reliable, and produces accurate and decently strong parts, there are some clear downsides. When zooming in, you can see the stair-stepping effect caused by the layer lines. This effect can be reduced by lowering the layer height, but it's impossible to completely eliminate it. Then there are overhangs and bridges. These often need supports, which are annoying to remove and generate unnecessary plastic waste. So why not use the full motion capabilities of our 3D printers? That's the idea behind non-planar 3D printing, using all three axes simultaneously to create more organic, curved layer paths rather than just stacking flat ones. In theory, this could solve many of the issues I just talked about. There are lots of approaches to non-planar printing, like conical slicing or special printer designs, some of them being quite complicated. But recently, Michael Wittrich and his team at the Zurich University of Applied Sciences published a paper about a novel slicing approach that caught my attention. It focuses on surface quality and also utilizes ironing for ultra-smooth top surfaces. It looked promising and can be used on standard machines. Since distances in Europe are quite reasonable, I took a train to Winterthur, Switzerland to visit Michael in his lab at ZHAW. He told me a bit about their story and how they got into non-planar 3D printing. Michael is part of the Institute for Mechatronic Systems, where they started their non-planar 3D printing journey back in 2016 with a 6-axis 3D printer. In early 2021, they released the RotBot, a modified Prusa MK4 with a 4th axis as a rotating toolhead. Through the RotBot project, they got into non-planar slicing, which is considered the key to true non-planar printing. From this standpoint, they developed the software further and finally introduced conical slicing. More about this can be found in a video from CNC Kitchen. That leads us to their recent paper called Adaptation of Conventional Toolpath Generation Software for Use in Curved Layer FDM. I tried to break it down in a few sentences. First, the curved top surface of the 3D model is represented by constructing a smooth interpolation over its mesh. Next, the model is geometrically flattened, so it can be sliced using a conventional slicer with planar slicing algorithms. Finally, the generated G-code is back-transformed by mathematically remapping the toolpath Z-coordinates and extrusion parameters onto the original curved surface, producing non-planar printing paths. For details, please refer to the paper, link in the video description. When I got back home from Winterthur, I wanted to try this non-planar printing method myself, so I upgraded some of my printers with longer nozzles to improve clearance and printing angle for curved layers. To give you an idea of the possibilities, I tried out different nozzles across various machines. For the new Prusa CORE One, I opted for this nozzle from non-planar.xyz. It costs about $19 in their online shop and is available with various thread types, including the popular V6. To install it on the CORE One, I used an extruder to V6 adapter, which fits perfectly. Another very good and convenient option is the Revo belt nozzle from E3D, which has an extra long tip. The Prusa MINI doesn't come with a load cell and still needs the inductive Minder sensor for bed leveling. Since it could crash when printing larger objects, there's a clever mod from Michael available on printables, which lets you slide the probe out of the way after leveling. This makes it way more convenient compared to loosening the screw and readjusting the first layer all the time. Last but not least, there's a cheaper yet effective option, such an airbrush nozzle. I had it left from my recent project in which I injected molten filament into the infill to create stronger 3D prints. It comes with a longer tip, giving it lots of clearance. You can find similar nozzles for just a few bucks on AliExpress, and they are compatible with most hot ends. Pro tip: to prevent leaking, make sure the airbrush tip is fully hot tightened. For installation on the Prusa MK4's extruder, I again used the V6 adapter to mount this airbrush nozzle. Before jumping into slicing my own models, I downloaded some pre-sliced examples from the internet to verify that my upgraded setups were working properly. While watching these stunning prints, let me quickly introduce the sponsor of today's video, PCBWay. PCBWay is your go-to online manufacturing partner for custom PCBs, 3D printing, CNC machining, sheet metal fabrication, and injection molding services. Whether you're working on a hobby project or a professional prototype, PCBWay has you covered with high-quality manufacturing and competitive pricing. Their platform makes it really easy. Just upload your files, get instant quotes, and enjoy reliable shipping worldwide. It's a smooth process that helps bring your ideas to life without the usual headaches. If you want to learn more and grab some special offers or vouchers to save even more on your projects, visit PCBWay.com, links in the description. Big thanks to PCBWay for supporting this channel and helping make videos like this possible. Let's get to slicing my own models. The installation is quite easy. You clone the repository from their GitHub, make sure to install the necessary packages in your Python environment, and click Run. The script opens a graphical interface that lets you select your STL, config files, slicing method, and a few more adjustments. It first transforms the STL, then uses the Prusa slicer installed on your computer to slice it regularly, and finally back transforms the output G-code. You can then open it in the G-code viewer. This is quite useful, as this method definitely has its limits, which we'll see later in the video. At first, I was a bit disappointed that there's no real slicer add-on, but for the current state of development, it's actually still quite user-friendly and gives you most options. There are some ready configs for printers like the Prusa MINI, DeltaQ, and MK4S in the GitHub. To add your own printer, simply export your profile from Prusa Slicing using Ctrl-E. Make sure to adjust the coordinate origin accordingly. Now let's slice and 3D print some actual models. At first, I downloaded some test models from the internet, like this blog from JanTec. The G-code preview looked good, which is why I started the print on my Prusa MK4S. The print looked very promising, so I decided to switch on ironing to see if it would improve the surface even more. The key idea behind ironing is to smooth the top layer by having the hot nozzle pass over it again, gently remelting the surface to reduce roughness and flatten layer lines. The ironing definitely smoothed the surface, but some parts still have a bit of a texture or roughness. This is actually something the paper talks about in detail. Because of the nozzle shape and how it interacts with the curved surface, the iron pass can push material forward unevenly. Basically, if the nozzle is offset slightly wrong or hits the surface at an angle, it can cause some small bumps or ridges. Material builds up in front of the nozzle, leaving those tiny imperfections behind. So while ironing helps a lot to reduce roughness, it's not perfect. Fixing this might require different nozzle designs or even multi-axis printers that keep the nozzle perfectly perpendicular all the time. Next, I sliced this wedge in 3 different ways: regular planar slicing at 0.2 mm layer height, non-planar slicing without ironing, and non-planar slicing with ironing. I think this is a very good demo of where the non-planar slicing approach shines. On angled surfaces like this, the stair-stepping effect looks rough and unappealing. It should also be said that with planar printing, it's almost impossible to get a dimensionally accurate, smooth surface, even with post-processing, because of the stair-stepping effect. As you probably know, I'm a rather technical person, so visual appearance doesn't matter too much to me. What really caught my attention was whether this non-planar method could bring some technical benefits beyond just smoother surfaces. There was this interesting experiment I came across on X where Pooch printed 2 ramps, one with regular planar slicing and one with the non-planar method, and tested how a steel ball rolled down each. The idea is that the stair-stepping in planar prints might create more friction or roughness that slows down the ball, while the smoother, non-planar surface should let it roll more freely. I printed these ramps myself and tried it out, but honestly, I didn't notice a big difference in how the ball moved between them. I designed and sliced some more relatively simple test models, but soon got to the limits of this approach. First off, the surface has to be mathematically continuous for the algorithm to work. No sharp edges, steps, or disconnected cuts allowed. If the surface is broken up, the script simply can't handle it. To give you a concrete example, a friend asked me to print such a cover for one of his machines. It had some cutouts that created non-continuous surfaces, and when I ran the Python script, it threw an error saying that it couldn't process the model due to these discontinuities. So yeah, while there's definitely room for improvement, especially around handling complex geometries and transitions, for now this method works best with relatively simple, smooth, continuous shapes. But honestly, it's still a fantastic technique to experiment with at home. You can grab the Python script straight from their GitHub, run it on your PC and start playing around. Plus, there are really affordable nozzle options out there, like that airbrush nozzle I showed, that make upgrading your printer for non-planar printing super accessible. Lastly, I asked Michael what their team is working on next. They are exploring new multi-axis printers like the 5-axis Warren V0 combined with ironing to push surface quality even further. They're also planning to build a larger 5-axis printer to expand what's possible in this space. So while non-planar printing is still evolving, it's an exciting step forward and I definitely recommend giving it a shot. I'd love to hear your thoughts or experiences with non-planar printing. Drop a comment and let's get the conversation going. Also, a huge shout out to my channel members TechGeek10, Thomas, Steve Bills and Toby Aumüller. Thanks for your awesome support. You make videos like this possible. If you found this video helpful, don't forget to hit like and subscribe to not miss any further videos here at JanTec Engineering.